Anyway, I'm Jason with Anderson Safety. We're the safety training partner for Oki 811. I go around with MG and Luis all over the state doing the Oki 811 safety days, and so I'm here today to do some confined space on our little virtual training day that we have here. So thanks for joining in. My background is oil and gas. Spent 10 years doing that before I switched over and started doing safety. And I have been I own Anderson Safety, and I've been here for the last 16 years. So that is kind of a little bit about my background, but we'll get into what you're actually here for, which is confined space entry. So MG, if you want to switch it over to the presentation, you can get my ugly mug off the screen, and we'll go from there.
You are all set.
Okay. All right. So when it comes to confined spaces, one of the biggest issues that I see and I deal with on a daily basis is identification of what a confined space actually is. So many people out there, they have policies in place where they just blanket call everything a permit required confined space, and that's not really how it should be, number one. And then number two, the other thing I see a lot of is people just don't actually know what a confined space is or how to define it or what the criteria have to be. So I always like to start off training going over what a confined space actually is. So to be considered a confined space, a space that you are going to enter has to meet 3 criteria. If it's missing any one of these 3 criteria, then it won't be considered a confined space. So that first criteria is size. A space has to be a confined space. It's got to be large enough that you can get your entire body into the space. There are plenty of spaces, especially in buildings and other places, where you might be able to stick your head in there, or a hand or an arm or a leg, but you can't really get your whole body into it. So it's got to be large enough and configured that you can get your entire body into it. So that's the first criteria. The next criteria is access. To be considered a confined space, it has to have limited or restricted means for entry and exit or access. There are a lot of spaces that are big enough to get into and that kind of thing, but they also have like full-size doors and things like that. So when we talk about restricted means for entry and exit, what we're really talking about is you've either got to crawl through some kind of hatch, you may have to go in and out via some kind of ladder, something like that. So the way you get into that space has some restrictions. Okay, so access is the second criteria. Our third criteria is going to be design. It is not designed for continuous employee occupancy. It's designed for you to maybe enter, complete a task or two, and then leave the space. It's not someplace that you're intended to work all day, every day, indefinitely. So temporary entry or temporary design for access to, maybe a certain electrical panel or something like that. So it's not designed for us to be in there all the time. We can go in, complete a task, get out. That's the intent behind a confined space. So if a space meets those 3 criteria, the criteria for size, access, and design, then it's classified as a confined space. That does not, however, make it a permit required confined space. To be a permit required confined space, it has to have some kind of a hazard associated with it. There are plenty of spaces out there that meet these 3 criteria. They're large enough to get into, they have limited access, and they're not designed for continuous occupancy. But there's also not any kind of hazard in that space. And so if there's no hazard, then it's not a permit required confined space. And I advise all of my clients that they not overclassify confined spaces by treating every confined space as though it was permit required. Most people end up getting themselves in more trouble than if they were to just classify that space as it is. So there are 4 specific hazards that OSHA is looking for a space to be considered permit required. The first of those is it contains or has a potential to contain a hazardous atmosphere. This is the biggest one. This is the most important one. The overwhelming majority of confined space incidents, deaths, those kinds of things in confined spaces, that's all due to air quality. Okay, so hazardous atmospheres are what cause the most accidents within a confined space. Okay, so that's the one we worry about the most. It's the one we focus on the most, but it's not the only hazard. So other hazards, if it contains or has the potential to contain a material that could engulf an entrant. We'll look at examples of all of these as we go through here, but it could be engulfed in a solid or a liquid. It is not specific to one or the other. So I'm not sure where everybody's from, but here in Oklahoma City, up kind of on the north side of Oklahoma City, there is a mile-long storm drain that is extremely large. It's a tunnel, actually. And so if you were to go in this tunnel and it were to start to rain, that tunnel will actually fill up from top to bottom, and that would engulf you. That tunnel, when I say large, it's large enough to drive, to facilitate two-way vehicular traffic through it, and it's about 12 foot tall. So wide enough for 2 cars to pass each other, and again, about 12 foot tall. So it's a very big tunnel, but it takes a lot of water, but it will fill up from top to bottom. So there are people that have to go in there periodically and clean up inside of that tunnel, make repairs to the concrete inside the tunnel and those kinds of things. And so because if it rains, there is that potential for engulfing an entrant, then they have to treat that as though it was a permit required confined space. If it has an internal configuration that could cause you to get trapped or asphyxiated, mainly by inwardly converging wall or floors that slope downward or taper to a smaller cross section. So these are things like hoppers and silos and things like that, where the bottom of that silo is cone shaped. If you were to go in there, you could slide to the bottom of it and you wouldn't be able to get yourself out. I'll show you some more examples of these as we go through. But so if you could get trapped in there because of how it's configured, then that would be treated as a permit required confined space. And then the last one is kind of a catch-all. If it's got any other serious safety and health hazard, if we're using chemicals in there, or if we're welding and creating welding fumes, or there's live electrical, we'll kind of look at all this stuff. Then the last one is kind of just that if it's got any kind of serious safety and health hazard, then we have to classify it as a permit required confined space. So to be permit required, it has to meet those first 3 criteria that we looked at for size, access, and occupancy. And then if it meets those 3 criteria and it has one of these associated hazards, then we would treat that as a permit required confined space. If it does not have one of these associated hazards, then it is not a permit required confined space, or we typically just call that a non-permit space. Okay, so it's a confined space, meets those first 3 criteria. There's no hazards in there, so we can treat it as what we call a non-permit space. All right, let's take a few minutes here to look at a little more in depth about the hazards that we encounter in confined spaces. We mainly divide those into 2 categories. We have our atmospheric hazards that you can see there on the left, and we have our physical hazards that you see there on the right. So we'll talk about each one of these as we go through here. But when we talk about atmospheric hazards, it's going to be oxygen, it's going to be toxins, and then flammable or explosive atmospheres. So those are the 3 main atmospheric hazards that we worry about. On the physical hazard side, it's going to be things like engulfment, configuration, other physical hazards like live electrical, steam, heat, moving parts, whether it's got some belts and pulleys in there that are guarded, things like that. Those fall on the physical hazard side. So let's look at these atmospheric hazards. We'll start with air. While our body uses oxygen, the air that we breathe is not pure oxygen. As you can see there, the air that we breathe is actually about 78% nitrogen. We're close to 21% oxygen, 20.9 here in Oklahoma, which is also the same as sea level. We're not high enough here in Oklahoma to be above sea level for it to change the oxygen percentage. So 20.9 is your oxygen percent at sea level. And then everything else that you hear about is the 1.1%. So that's your carbon dioxide, carbon monoxide, all the other, some are pollutants, some are not, that kind of thing. But all of that falls into that 1.1%. Our oxygen level, though, can go two different directions. We can have oxygen deficient atmospheres, and then we can have oxygen enriched atmospheres. So if it's oxygen deficient, then we're not going to have enough air to breathe, and we will suffocate inside of that space. On the other end of that spectrum, if it's oxygen enriched, that can cause some breathing problems. You can hyperventilate by getting too much oxygen into your system, so that is one concern. But oxygen-enriched atmospheres also become highly flammable atmospheres as well. So when you increase the amount of available oxygen around flammable and combustible materials, those materials will ignite at lower ignition temperatures. They will burn hotter and faster. And so oxygen-enriched atmospheres also increase our risk of fire or explosion if there's anything flammable and there's any kind of ignition source. So how much air do we actually need? Well, 19.5 is the minimum acceptable level for entry into a confined space. However, if you put a meter on a space and it's reading anything less than 20.9, then something in that space is using oxygen, or there's not enough ventilation into that space to maintain a suitable oxygen level. So even though you may be above the 19.5, which would be within the parameters of entering that space, you need to find out why you're not at 20.9. Is it just because the space has been sealed up for a long time? It just needs to ventilate for a few minutes, and then it will equalize and the oxygen level will go up. Is there some kind of chemical in there that is consuming oxygen? Something like that. You need to investigate why your meter is not reading 20.9 if it's not. Don't just assume, oh, he said 19.5 was the minimum. We've got 19.7, so we're good to go. Clearly, the oxygen level is below normal, and you need to know why. If something is consuming oxygen in there, you may enter when it's 19.7, but after being in there for a few minutes, that oxygen could continue to decrease, and then all of a sudden it's well below 19.5, and you're going to have some issues there. So at 15 to 19%, that's going to decrease your ability to do work. It's going to feel like you're in Denver or climbing up Pikes Peak or something like that. So you're going to start breathing heavier, and you're not going to be able to do as much work as what you would normally be able to do. It's also going to cause some issues with your coordination. So we see decreased coordination as well. And then you'll have early symptoms of oxygen deprivation. You may be a little lightheaded. You may get a little bit of a headache. You may become dizzy, that kind of thing. So you'll see some very early symptoms of not having enough oxygen going to the brain. At 12 to 14% oxygen, your respiration is going to go up tremendously. Your judgment is going to become very poor. You may not even be able, even at 12 to 14%, you may not be able to recognize that there's an issue. So you're not going to be able to think rationally at that point. And so you're going to start making some very bad decisions. At 10 to 12%, your respiration is very labored. Normal respiration rate is 16 to 18 breaths per minute. you're going to be much, much higher than that. So your respiration rate is going to go up tremendously. Your lips are starting to turn blue. You are suffocating at that point. You are running out of oxygen. At 8 to 10%, though, you'll have complete mental failure. You won't be able to recognize that you're in trouble when you get down to that level. And the problem with that is when you get down to that level and you have that mental failure, you don't know that you need to get out of that environment and that you need to be rescued. There's a good chance at 8 to 10% you're gonna become unconscious. You'll become nauseous. You may even vomit. Those kinds of things. So you're gonna collapse relatively quickly. At 6 to 8%, this we start dividing up into time. Time becomes much more of a factor when you get down to 6 to 8%. So 4 to 5 minutes and 6 to 8% air. There is possible recovery from that if we get you out in time. There's a good chance that you're probably going to have some permanent mental impairment due to lack of oxygen going to the brain for an extended period of time, but you might be able to survive. At 6 minutes in that atmosphere, it becomes 50% fatal. So about half of the people will die if they're in there for 6 minutes. And then once you get to 8 minutes, then it's 100% fatal. Nobody can survive longer than 8 minutes in a 6 to 8% oxygen atmosphere. If it drops even lower than that, you get down to 4 to 6%, you're going to go into a coma almost instantaneously, and you're going to die shortly thereafter within just a few minutes. You will not have any oxygen. So it's kind of what we look at. If you're not aware, in 2023, we had a couple of different fatalities involving confined spaces here in Oklahoma. One was up in North Edmond, north of Oklahoma City, and the other one was down in southeastern Oklahoma at a church camp down there. The one down at the church camp involved H2S, but the one in Edmond, that one, it killed 2 people and almost killed a third. But that one, the oxygen level was extremely low. That was a oxygen deficient atmosphere that those guys went into. They had just pulled what's called a vacuum test on a manhole. That is where once a manhole is complete, they plug the lines, they pull a vacuum on it to make sure, because manholes are not all one piece. They're put in pieces with seals. And so to check the seals, they pull a vacuum on the manhole. In other words, they suck all the air out of it. That manhole was about 25 foot deep approximately, and about 6 to 8 feet of it was sticking up above grade because it was in a floodplain. So when they released the vacuum normally when you release a vacuum off of a vacuum test on a manhole, it will oxygenate almost instantaneously. I've done testing immediately following vacuum tests, and the oxygen had returned to normal in the confined spaces that I tested. The oxygen level had returned to normal by the time we could pull the lid and I could drop a hose down there, which was virtually simultaneously. So they typically oxygenate very quickly. This particular one did not. They did not put a meter on it and check it, and so a couple of guys went down in there. They were down below 10% oxygen in the bottom of that. My guess is they were probably at 6 to 8%, somewhere in that range. And it took 2 of them. A third guy went part of the way down and started having trouble breathing, and so he came up before he got to the point of passing out or anything like that. So a third guy actually went in there. So we almost lost 3 people there. So oxygen is very important. We don't go into any confined space if we have not tested it and put a meter on it. Other common atmospheric hazards that we see, carbon monoxide is one of those. If we have any generators, any vehicles, things like that, hanging out close to our confined space, then carbon monoxide from the exhaust can get pulled down into the confined space. and cause some issues. It is slightly lighter than air, which means normally it would kind of float away. But if there's any kind of vacuum on your manhole or on your confined space, then that vacuum can pull that carbon monoxide in there. Or if you set up your confined space ventilator close to some type of internal combustion engine, then your ventilator could pull in some carbon monoxide and put it into your space for you. So that's typically how we get carbon monoxide in there. Not usually as serious of an issue. Not that we should stay in that. It's got a little higher PEL at 50 parts per million compared to that of H2S. It's IDLH at 1,200 parts per million. And so we have some limits there. As long as we stay below those limits, we're okay. The next big one, if you deal with any kind of sewer lines or anything like that, storm drain, sanitary sewer lines, H2S is a real possibility. H2S smells like rotten eggs if you can smell it. It is a neurotoxin, so when you inhale H2S through your nose, it will deaden the nerve in your nose that sends odor signals to your brain. So you can't always smell it, even though it does typically have the sulfur causes it to smell like rotten eggs, but only at low concentrations can you smell it. At higher concentrations, the nerve in your nose is going to get deadened, and you're just not going to be able to smell it. H2S is extremely deadly. It has a very low PEL at 10 parts per million. It does become IDLH at only 100 parts per million, and it becomes extremely, extremely fatal when you get up to just 600-700 parts per million. So H2S and methane, we'll look at methane next, but both of them, H2S and methane, are the result of the decay of organic matter. So when we're dealing with storm drains, sanitary sewer lines, there is organic matter going into those lines, and if it's ever allowed to sit and decay, then it will create that H2S and that methane. They usually go hand in hand. So I'm going to be very careful with H2S. And then flammables. So any type of flammable, and methane is the most common one that we deal with, but any type of flammable is going to have both a lower explosive limit and an upper explosive limit. And if the concentration is between those, then that flammable is in its combustible range. When your concentration is below the lower explosive limit, then you don't have enough fuel. You've got too much oxygen. We call that lean, and that will not combust. On the other end of the spectrum, if you're above the upper explosive limit, that means you have too much fuel, not enough oxygen, and we call that too rich. If you remember carburetors from the 1980s and earlier, if you put too much fuel into your carburetor, or your motor, you would flood your motor. And that was a situation where your automobile engine had too much fuel and not enough air for it to run properly. So you were above the upper explosive limit in that situation. We don't ever want to wait till the concentration gets to the lower explosive limit before we evacuate a confined space. So we should always be monitoring our confined space if we have the potential for flammables. And if we do, our alarm is going to be set to go off at 10% of that lower explosive limit. And that's to allow us time to get out of there, get out of that space before it actually reaches that lower explosive limit. Because once it reaches the lower explosive limit, a fire is now a potential. The last kind of major atmospheric hazard we see in a lot of confined spaces, especially if you're dealing with water and sewer lines and things like that, it's going to be methane. So methane comes from the same place as H2S. It's just due to the decay of organic matter. It's colorless and odorless when you in nature. if you think you can smell natural gas, that's because they add an odorant to it at the processing plant before it's piped to like your house or your business or whatever. But naturally occurring methane is going to be odorless. You're not going to smell it. It has a very, very lower explosive limit at only 5% or 50,000 parts per million. But it also has a really small combustible range of just 10%. So, excuse me, methane is only flammable or combustible when the concentration is between 5 and 15%. So very small range, but also very low range. So our alarm will let us know if methane reaches 5,000 parts per million. That's 10% of our 50,000 part per million lower explosive limit. So that's when your alarm will go off at just 5,000 parts per million of methane. Okay. Other chemical hazards that can give off, create atmospheric issues, any kind of chemical contamination of surfaces, anything that can be absorbed through the skin, be ingested, be inhaled, things like that. These can cause irritation, chemical burns, have systemic toxicity. So any other chemicals that go in there, remember, you're not going to have, normally you wouldn't have a lot of ventilation in there. So if you don't put ventilation in and you have a chemical that is giving off vapors, it's going to, the concentration is going to go up pretty quickly. So we have to be very careful of any other chemicals that we might take into a confined space. We're getting into the physical hazards now. So this is, we'll talk about engulfment for a second here. Again, it can be engulfment of a solid or a liquid. It does not have to be one or the other. You can see there in the photo on the left, the diagram on the left, we see this at harvest time. We usually have a fatality or two of people getting buried in grain bins. Basically what happens is the grain is pulled from the bottom by an auger. This creates a cavity in the grain. So the grain has sloped sides there. If it's too humid inside of that grain bin, then some of that grain will stick together because of the moisture in the air and create what's called a grain bridge. And that grain bridge is very, very weak. And so if somebody were to go in there and stand on that grain bridge, they would collapse it. They would fall into that cavity, and then additional grain would fall in on top of them. And it's no different than it's just like being caught in a trench collapse of an excavation. It's the exact same thing. Then on the other side, we can have liquid engulfment. What you're looking at there is a lift station where they have had to go in and make some repairs. That's why that ladder is in there. But you can also see that a lot of water can come into that lift station very, very quickly. And so if somebody were down there and a valve wasn't closed properly and we had a bunch of water come in, that could potentially engulf somebody that was down in that lift station. So that's another example of how you could be engulfed in something. This is what we talk about when we say configuration hazard. This is what's called claricone. It's at a water treatment facility, and so a claricone just helps clarify the water before it goes out for consumption. This particular crew, if you can see the two guys standing down there in the bottom left, and then there's one guy up in the area lift up there that's getting ready to go in there. They had to go in and completely sandblast the inside of this and put a new coating on it to protect it. And as you can see there, without the proper equipment, he could actually get stuck in the very bottom of that cone. And so we had to make sure that he had adequate access and egress via his ladder. We had to make sure that his ladder went all the way to the bottom so that if he were caught down in the bottom, that he would be able to use his ladder to climb out of it. Without the ladder, you get trapped down there on the bottom. So that is what we consider a configuration hazard. Other physical hazards, if you have any kind of exposed live electrical, augers, blades, turbines, pumps, things like that, steam lines, chill water lines, stuff like that. Maybe belts and pulleys, chain and sprocket, all of that kind of stuff. If you're exposed to any of that within a confined space, then those fall into that kind of catch-all other physical hazards category. And then in Oklahoma, we deal with these. We have 3 venomous snakes in Oklahoma, and we have 2 main venomous spiders. Fortunately, those spiders don't cause fatalities, but we do have 3 snakes here in Oklahoma that are capable of causing a fatality. Oftentimes, if you open up confined spaces that are out in the environment, you will find some of these little critters hanging out. So you've got the black widow there on the right. Her venom is a neurotoxin, so it's just a very, very painful. It will cause a lot of swelling and stuff like that, redness in the bite site, as well as extending beyond the bite site. So just a very, very painful bite with her. The one there in the middle is the brown recluse, also a painful bite, but not a neurotoxin. The venom from the brown recluse will actually, it's corrosive to flesh, and so you'll have a very big kind of pitted out sore around the bite site on that one. And then snakes. So we have 3 venomous snakes that we deal with here in Oklahoma. We're all aware of rattlesnakes. We also have copperheads. And then we also have cottonmouths, or some people call them water moccasins, but same thing, cottonmouth. All 3 of those snakes are capable of causing death to an adult human. So if you get bit by one of those, you need to seek medical attention very, very quickly. I do recommend, if you get bit by a snake and you think it might be venomous, go to more of a rural hospital. If you go to OU Med downtown, they're not going to be as likely to carry the antivenom for rattlesnakes and copperheads. Whereas if you go to a smaller, more rural hospital, they keep the antivenom in stock because they deal with those kinds of things all the time. So, but we have those. And if you're not aware, we do have some alligators. The American alligator is starting to migrate into far, far southeastern Oklahoma, down around Idabel and that area. They have found an alligator as far north as the port of Catoosa. And then there are some people that are claiming that they have seen alligators in Lake Texoma as well. So if you go down around those areas, alligators are now something to be concerned with. So just be aware of that. Fortunately, the American alligator is not that aggressive as long as you stay away from them. They're not going to chase you up the road. They're pretty laid back, pretty chill. I'm not saying go pet them, but they're also not necessarily going to attack you unless you just get way too close to them. So just be aware those things are out there. Next thing I kind of wanted to review is a little bit of our entry equipment. First of all, nobody in any of your companies should be doing what true permitted entry. There are, for permit required confined spaces, there are 3 sets of entry procedures that we're allowed to choose from. Okay. And so the worst of those is doing a true permitted entry. The only time a true permitted entry is done is when the hazards within that confined space cannot be eliminated. And so if you're doing a true permitted entry, it means that you are going into a space that has a hazard in the space, and that hazard cannot be eliminated. So we want to avoid that. So let's look at a little bit of the entry equipment that we would need if we were doing even just a normal alternate, what we call an alternate procedures or reclassification or a non-permitted entry. The first thing you're going to need is a gas detector. There are two different types. There are meters and monitors. What's pictured there is a meter. The difference between a meter and a monitor is that a meter has a pump on it that is continually pulling air through the meter and forcing that air over the sensors, so it is actively checking the air at all times that it's turned on. Okay, that's a meter. A monitor does not have a pump, and it is passively monitoring the air in the sense that the monitor is turned on, but it is simply waiting for the chemical contaminant to come into contact with the sensor. A monitor does not draw air into it. It does not force that air over the sensors. And so it is not actively monitoring the air. Only a meter does that. Monitors are just fine for the entrants to monitor their space while they're in there working. However, prior to entry into any space, that atmosphere has to be checked with a meter, not a monitor. And that's a big issue that I see. I see a lot of people, they have 4 gas personnel monitors that they wear on their shirt or on their collar or whatever. And they will take that off and they will put a piece of rope on it or string on it, and they will lower that monitor down in their confined space. That is not the proper way to check the atmosphere within a confined space. If that monitor were to alarm and go off, by the time they pull it out of the space and actually look at it, the air is going to be back to normal. And so they're not going to know what caused that monitor to alarm. So meters are what we should always be using. You can see there the yellow device is the meter itself. Up in the top left of the case, you can see a hose up there. There's right next to the meter, there's a short hose. So these typically, when you buy them, they come with a long hose and a short hose. And so that is to allow you to drop the hose into the space, hold on to the meter while the hose, while air is pulled through the hose. And then you can, if the meter alarms, you'll be able to know what caused it to alarm. Okay. So all confined spaces must have an atmospheric check on them. You cannot make a determination as to whether you have a non-permit space or a permit space if you haven't checked the air. So every confined space before entry gets the air checked on it, no matter what. Even if you think it's going to be a non-permit space, you still have to check the air. Okay. So if you're doing any kind of confined space entries, you will have to have a gas detector, preferably a meter. Then more than likely, if you're doing confined space entries, you're going to need some ventilation. Okay. Ventilation, the idea behind ventilation is to push clean air in. We don't ever suck air out. If you suck air out, you can cause that space to become oxygen deficient. Okay. So we want to push clean air in. This is typically, this would be for a vertical entry space where our entry point is on top of the space. We want to make sure that that blower, the intake on the blower, has plenty of clean air. We don't want that intake being close to any kind of exhaust, generator, running vehicle, other equipment, machinery. It needs to be out in the open where it has access to plenty of clean air. And then the hose coming off of it, we want to get the hose as far down into the space as possible. We want to dilute from the bottom, creating positive pressure inside the space that will push air up and out of the space. Okay, that's what we're trying to do with our ventilation. If you were to just put that hose at the very top of the space, it wouldn't create enough positive pressure. It wouldn't dilute the space enough, and the air going in through the hose would just go right back out that exhaust port, if you will. So we want to make sure that hose gets as far down into that space as possible. We always dilute from the bottom, create positive pressure inside the space, and push any kind of dirty air out of the space. When you set up these blowers, we want to, first of all, that's an accordion hose that comes off of the blower. We want to stretch the accordion hose all the way out, whether we need it all the way out or not. When you scrunch those accordion hoses up, then it shrinks the inside diameter of the hose and it restricts the amount of air that can flow through there. So always stretch that accordion hose out as far as you possibly can, because we want the inside of that hose to be as large as possible to push as much air through it. Then the second thing, I want to make sure I minimize the number of bends in the hose. Every time you put a bend in a hose, you are going to reduce the amount of airflow going through the hose. So, in fact, every ventilator will have a label on the side telling you how many cubic feet per minute of air it can push. And so it'll say 0 bends, 190-degree bend, 290-degree bends. And you will notice that the airflow goes down with each bend. So that's to let you know, if you put 2 90-degree bends in your hose, this is the amount of air you can expect coming out of the other end. And it will be reduced from a straight hose. Okay. So like this picture here is a good example of kind of what not to do. They took the hose, they put a slight 45-degree bend in it to go up and over that bar. At that bar, they've got a full 90-degree bend, if not a shade more than 90. And then there's another slight bend just inside the manhole there. So they put basically 2 45-degree bends and a 90-degree bend in that hose. And so that's restricting the amount of air. Where if they had ran that hose underneath that bar, then it would have only had the 1 90-degree bend going into the space. And that would have facilitated more air flowing through that hose. So make sure you pay attention to how many bends you have in your hose. There definitely should not be more than 2. 1 90-degree bend should be all you have in your hose. And again, stretch it all the way out so that the inside of that hose is as big as possible. And then always make sure that the intake on your ventilator has access to fresh air. Okay. All right. We have about 10 minutes left, so I wanted to go over some basic entry procedures. These are going to be entry procedures for, we're not going to go through permitted entry procedures, okay? Because you guys should not be doing that type of work. If you are, you're going to need a whole lot more training than a 1-hour webinar. So keep that in mind if you need to actually do a permit required entry. Okay, so the first thing you have to do is identify the space, determine if anybody's going to be in it, and if the answer is yes, determine if it's going to be permit required. Okay, so we have 3 options for entering permit spaces. There's really only one option for entering non-permit spaces because we don't have to really do much if it's a non-permit space. So we are going to look at non-permit and then alternate and reclassification. The pre-entry certificate, that has to be filled out on every space regardless. This is how you determine, this is the form that you use to determine classification of your space. So you're going to walk through and identify any potential hazards. You're going to document what meter you used to test the air. You're going to document what your air readings were. These should be 20.9000. That is what we are looking for. And if that is the case, then we're going to sign off on it and we can classify it as either a non-permit space if everything's good and there's no hazards, or if it's a space where only the atmosphere is our only concern, then that's when we use our alternate procedures. Okay, so entering non-permit spaces. We're going to evaluate that space. You're going to still fill out your pre-entry certification to document your test, your atmospheric tests. And then if everything's good, we're not worried about any atmospheric hazards. There's no potential for an atmospheric hazards. We don't have any physical hazards in there. Then we can just enter the space. We can come and go as we need. No additional work needs to be done there. So that's for a non-permit space. So let's say we have a permit space, but our only concern is the atmosphere. If that's the case, then we use what we call alternate procedures. So we do our tests, we check the air, we fill out our pre-entry certification. Then after we've done that, we're going to put continuous forced air ventilation on it. So we're going to put a ventilator on it. And then we're going to continuously monitor the space. So you're going to have a meter, or in this case, you can use the monitors that the individual entrants actually use. Or the entrants can use monitors when they go in the space. That's fine. That's considered continuous monitoring. Okay. So to do alternate procedures, fill out your pre-entry cert, put your forced air ventilation in place, monitor the space. If any alarms go off, everybody gets out of the confined space. Our last set of entry procedures that we'll look at here, if I don't have any atmospheric hazards, but I have some physical hazards, maybe I have some live electrical, maybe I crack open the lid and there's a freaking rattlesnake in the bottom of it. If I can eliminate those hazards, then I can reclassify that space as a non-permit space. Okay, but I'm only allowed to do that if I have no actual or potential atmospheric hazards, and I only am concerned about physical hazards, and those physical hazards can be eliminated. Okay, if I can do that, I can reclassify the space. It's now a non-permit space once the physical hazards have been eliminated, and entrants can come and go out of the space as they need. Okay, so those are our procedures. Again, none of your employees, you should have policies in place that state that employees are not allowed to make routine entry into permit required confined spaces. Most people are not set up to do that. If you have to do a true permitted entry, you're going to have a rescue team. That requires rescue training. You're going to have people trained in first aid CPR. So you're going to have first responders available. There's a lot of equipment that you have to facilitate rescue. Your rescue team has to regularly, annually practice making confined space rescues. So there's just a lot to be done to actually do a true permitted entry. So we want to avoid those. And it's just not safe to do permitted entry even with a permit, because you still have employees going into a confined space that has a hazard present. And we should not be going into confined spaces with hazards present. All right. Okay. I will open it up for questions, or if you want to throw them in the chat, you can do that as well. Does anybody have any questions, comments, concerns?
Jason, I just threw you and I both into the presentation window as well. So far in the chat, we haven't had a lot of activity. If there are any questions, let us know. We show that there's 15 people who've learned a little bit about confined spaces today. Couple things I do want to point out. This is just a small portion, and it's a sample size of confined space training in reality. Jason has been our training safety partner for a couple of years now. I do recommend, if your organization needs training, first of all, come to one of our safety days. You get the best of both worlds. You get OK, everyone, and Jason. But Jason's always available to help you out directly if necessary. So definitely keep tabs on both of us for all your safety training needs. If you do have any questions, I understand this was a one of our longer sessions. Probably a lot of brain fatigue after a long day of safety like today. So if you do have any questions, you can always follow it up by shooting me an email at education@ok11.org. Also, Jason's contact information was on his bio. And if you don't see it, just email me and we'll get it to you. So with that, it is 1:59. Jason, even with our late start, the perfect timing. And so I appreciate you. And again, to our attendees, if you have any questions, feel free to follow up with us and we'll be happy to reach out to you. And hopefully a lot of you will be in Tulsa for our next Tulsa Safety Day, which is August 13th. So thanks, Jason. Thanks for all the information you shared.
You're welcome. Thanks for having me today, guys. Appreciate
All
it.
right. Thank you, everybody.
Bye-bye.